Hi, Mr. Green here. I'm going to be taking you through the next section of the AQA Physics GCSE Forces topic. This is on the conservation of momentum, and your learning objective is to state and apply the principle of conservation of momentum. Please pause the video whilst you take that down as your title. Okay, some retrieval questions to start with, all around momentum. If you pause the video and attempt these 5 questions, then restart when you'd like the answers. Okay, question 1. The equation for momentum is momentum equals mass times velocity. The units of momentum are kilogram meters per second. What type of quantity is momentum? Momentum is a vector quantity because it has direction. How do we assign direction in momentum calculations? Well, one direction is assigned a positive value and the opposite direction has a negative value. What's the momentum of an object that's moving at 30 meters per second with a mass of 20 kilograms? That would be 20 times 30, giving us a momentum of 600 kilogram meters per second. Okay, so today we're going to explain what's meant by a closed system, we're going to explain the principle of conservation of momentum, and we're going to apply that principle. So, a system in physics is defined as a collection of objects that we choose to model with our equations. So, any objects that are interacting with each other we would call a system. So when we talk about maybe throwing a ball up and down in the air, the ball is part of that system. When we talk about two objects colliding with each other, the two objects are part of the system. Now there's two types of system. There is a closed system and an open system. In the closed system, nothing can get in or out, including energy. Now as a result of this, the total amount of energy within that system remains constant. Even though the types of energy may change, the total amount of energy in the system remains the same. So if we say we throw a ball in a closed system, that means the energy changes between the ball and my hand are constant. There's no wasted energy out from there. In an open system, energy and other factors can be added or taken away from the system. So as a result of that, the total amount of energy within the system must change or will change as energy is added or taken away. Now when we study examples for conservation of momentum, we'll be assuming we're working in a closed system. No energy is added or lost during any interactions. So, conservation of momentum. Moving objects interact with each other in a number of ways. So they might collide, they might explode, they might glance onto each other. Now when such an interaction occurs with moving objects, momentum is always conserved within a closed system. That means the momentum in the system before the interaction is equal to the momentum after the interaction. So momentum before a collision, before an interaction, before an explosion is the same as the momentum after the explosion, after the interaction. So the total momentum before something occurs is the same as the total momentum after it. Okay, 3 questions to start on with your progress check. If you could answer all 3 questions and unpause the video when you would like to have the answers. Okay. A system in physics, that is a collection of objects we choose to model with our equations. What is meant by a closed system? That's in a closed system, nothing can get in or out, including energy. And what's meant by the conservation of momentum? The total momentum in the system before an interaction is equal to the total momentum in the system after the interaction. Okay, 2 objects in the below example collide. Now as you can see, we don't know the velocity of the final object, the 2 kilogram object, after the collision. But because of the conservation of momentum, we can work this out. Remember, total momentum before the collision is the same as the momentum afterwards. So if we can work out the total momentum before, we know the momentum afterwards, we can then break it down. So, what is the total momentum before the collision? Object 1, momentum is mass times velocity. It's got a mass of 1 and a velocity of 5. So its momentum is 5 kilogram meters per second. Object 2 is not moving, so its momentum is 0. The total momentum before the collision then is 5 kilogram meters per second. That means the total momentum after the collision is also 5 kilogram meters per second, because momentum is conserved. So what's the momentum of object 1? We know its mass and we know its velocity. Let's work that out. 1 times 1 gives us 1 kilogram meter per second. This means object 2 must have a momentum of 4. Because object 1 only has a momentum of 1, and we know the total momentum has to be 5, because it has to be equal before and after a collision, it has to be the same. In order to make it up to 5, the momentum of the 2 kilogram weight must be 4. From that, we can now rearrange the equation and calculate the velocity of object 2. Rearranging it, velocity is momentum divided by mass. That gives us 4, which is momentum divided by 2, giving us 2 meters per second. Now that's positive. It's not negative, so it moves to the right. Okay, with that in mind, could you answer those 2 questions? Calculate those missing values and pause the video when you'd like the answer. Okay, so for the first one, the 8 kilogram mass is moving at 1.07 meters per second. For the bottom one, the 5 kilogram mass is moving, to the right, the kilogram is moving. And the bottom one, the 5 kilogram mass is moving at 2 meters per second to the right. Try for these 2. Pause the video and restart when you'd like the answer. Okay, so for the 200 gram mass at the end, that would be 1.25 meters per second to the right. And for the 12 kilogram mass on the fourth one, that would be 14.5 meters per second to the right. Example 2. What's the final velocity and direction of the 2 kilogram mass? If we see, we're taking direction into consideration. For the first one, 1 kilogram at 5 meters per second to the right. Second one, 4 meters per second to the left. As you say at the bottom there, when it's travelling to the right, we give it a positive value. When it's travelling to the left, we give it a negative value. So momentum of the first one is 5 kilogram meters per second. Momentum of the second one is minus 8 kilogram meters per second. It's 2 times minus 4. It's travelling in the opposite direction. So to assign that, we give it a negative. So overall, the total momentum is minus 3 kilogram meters per second. 5 add minus 8 would give us minus 3, which means the momentum on the right-hand side also has to be minus 3 kilogram meters per second. Let's work out the momentum of the 1 kilogram mass. That's minus 2. So what must the momentum of the 2 kilogram mass be? In order to get it to minus 3, it's got to be minus 1 kilogram meter per second. Velocity is momentum divided by mass, so we do minus 1 divided by 2, giving us velocity of minus 0.5 meters per second, showing it's going to the left. Okay, with that in mind, could you answer these questions? You need to assign a direction and a speed. Pause the video. Best of luck. Okay, so for A, 1.25 meters per second to the left. For B, 6.66 meters per second to the right. And C, 200 meters per second to the right. Next one, let's say 2 trolleys collide and stick together. From the data below, let's calculate their velocity after the collision. So there's our trolleys. Trolley A's got a mass of 3 kilograms and a velocity of 8 meters per second. Trolley B has a mass of 5 and a velocity of minus 4 meters per second. It's moving in the opposite direction. Momentum of trolley A is 24. Momentum of trolley B is 20. That means our overall momentum is 4 kilogram meters per second. 24 add minus 20. After the collision, total momentum will also be 4. But because they collided and they've stuck together, they've changed the mass. The mass is now 8 kilograms. We know the momentum after collision has to be 4. Momentum divided by mass gives us velocity, which is 0.5 meters per second to the right. It is a positive correlation. Okay, could you answer the missing values and the... So we want the momentum of the new mass. So give us the new mass, give me the speed, give us the momentum. Off we go. Okay. The object would then weigh 32 kilograms for A, and it would have a speed of 4.68 meters per second to the right. For B, the new object would be 9 kilograms and have a speed of 2.22 meters per second also to the right. For C, it would weigh 13 kilograms and have a speed of 1.53 meters per second to the left. And for D, 200 kilograms times 4 would give us 500 kilograms when it's joined together as the mass, and it would be 1.6 meters per second to the right. Finally, explosions. Like any interaction where movement's involved, momentum is conserved before and after an explosion. So, what's our missing value here? What would the speed of that 15 kilogram fragment be? What's the velocity of it? Momentum before the explosion is 0 because the object isn't moving. If 20 times 0 gives us nothing. So momentum after the collision must also be 0. So if we calculate the momentum of the 5 kilogram mass, then the opposite must be true of the 15 kilogram mass. Momentum of the 5 kilogram mass is minus 35 because it's going to the left, times 5, giving us minus 175. In order to ensure that momentum is conserved and it would be 0 afterwards, that means the 15 kilogram mass must have a momentum of 175. We then rearrange our calculation. Momentum divided by mass gives us velocity. That is 11.7 meters per second to the right. Okay, could you answer the missing values on here? Work out the final velocities. Okay, so for the first one, it would end up with a mass of 17 and a velocity of 0.88. Second one, a mass of 3 and a velocity of 1. Third one, a mass of 20 and a velocity of 45. And the fourth one, a mass of 150 and a velocity of 1. Okay, I hope that was useful for you all. Please check through all the videos on our YouTube channel and subscribe for any changes. Hope it's been useful. See you soon. Goodbye.